All right, well, this is the beginning of chapter 11. I wanted to get started here. We're going to talk about intermolecular forces, and so to do that, we're going to need to first start and talk about some of the key differences between solids, liquids, and gases. So here we're going to start by looking at gases, liquids, solids. We'll find that gases are what we refer to as a dispersed phase. And by being a dispersed phase, what that means is that the molecules are really far apart. And that liquids and solids will refer to those as being condensed phases. Well, we'll find that in gas, a dispersed phase, it's going to have very weak intermolecular forces. Whereas in liquids and solids, it's going to have very strong intermolecular forces. So that's going to be one of the important distinctions. This chapter is essentially all about liquids and solids. Chapter 10, if you go back and look at it, it's about gases. So the very first thing that we want to look at is we want to review some of the properties about solids, liquids, and gases. And I'm just going to go through these real quickly. So as far as volume and shape characteristics, we will find that gases will assume both the volume and shape of its container, whereas liquids will assume the shape of the container, but it does not assume the volume of that container. Solids, on the other hand, are going to retain their shape and volume. So that's each one of those acts differently in the volume shape characteristics. Related to this, we'll find that gases will expand to fill whatever container, whatever space is available, whereas liquids will not expand to fill their container, and solids also will not expand to fill their container. We will find that gases are compressible, whereas liquids and solids are virtually incompressible. Now, I do say virtually incompressible because if you push hard enough on it, you can get it to compress, but we're looking at under normal kinds of conditions. As far as does it flow, gases will flow, liquids will flow, solids do not flow. And then finally, we'll find that within a gas, we can get very quick diffusion. With liquids, we get slower diffusion, but definitely it does occur. And with solids, diffusion is so slow as to be just ridiculously slow. So we're going to look at number 11.1 on the in-class assignment. And so here I'll switch over. Here I've got the in-class assignment. All right, and you'll notice I've included both chapters 11 and 12 on this in-class assignment, and that's simply because these used to be together, and so now we want to, I just leave them together on the in-class assignment. So here we want to see, does it assume the shape of its container? Well, we'll look for a solid, nickel solid. We will find that no, it does not assume the shape of its container. But for H2O liquid, since it's a liquid, yes, it will assume the shape of its container. And gases also will assume the shape of its container. Does it flow readily? No, solids do not flow. Liquids, yes, they do flow. And gases definitely flow. All right, is it compressible? And again, we mean, is it compressible under sort of normal conditions? We'll find that solids, no, are not compressible. Liquids are not really compressible, but gases are compressible. All right, will it expand to fill its container? Well, we'll find that solids and liquids, no. So no, will not expand to fill its container. The liquid, no, it will not expand to fill its container. But gases, that is a key characteristic of gases, that it will expand to fill its container. All right, does it allow molecules to diffuse easily throughout? Well, again, for solids, no. For liquids, we're going to go ahead and say yes on this. Even though it's slow, we're going to say that it will diffuse. And that for gases, we will definitely say yes. and then has strong intermolecular forces. Well, we'll find that condensed phases of solids and liquids do have strong intermolecular forces, so yes and yes, whereas gases, no, they do not have strong intermolecular forces. All right, well, now that we've done that, we're going to go back and we want to look at the difference between intermolecular forces and intramolecular forces. Intramolecular forces are going to include mostly covalent bonds. And so a covalent bond, like between this hydrogen and chlorine and the hydrogen chloride molecule, is quite strong. And in fact, for this one, I remember the number, it comes out to 431 kilojoules per mole. So over 400 kilojoules per mole for that strength. Whereas there's an interaction between the molecules that's called an intermolecular force. And that one is quite weak in this, relatively weak. We'll find that the strength of that interaction is somewhere on the order of about 10 or 15 kilojoules per mole. So much, much weaker. We want to look at the different types of intermolecular forces, and I'm going to show them to you in increasing strength. And so I'll put these numbers up here, and then we'll talk about each of these categories. So here we'll start with London dispersion forces. Now there's a pretty big range of how strong a London dispersion force can be. And we're going to talk about this in more detail later, but just to kind of give you a ballpark of how strong each of these are. For London dispersion forces from about 0.1 kilojoules per mole up to about 30 kilojoules per mole. For a dipole-dipole interaction, we'll find that those typically are stronger. The usual range is from about 2 to 15, but you'll see there's quite a bit of overlap with the strength of the London dispersion forces. But generally speaking, we'll find that the dipole-dipole forces are stronger. For hydrogen bonding interactions, which is a special type of dipole-dipole interaction, we will talk about that here in a little more detail later. We'll find that it's a bigger range of possibilities from about 10 to 40 kilojoules per mole, so much stronger. Well, we'll also look at ion-dipole interactions, which typically range greater than 50 kilojoules per mole. There's a very broad range here, so I just give that approximate number. And then ionic bonding, which we talked about way back in Chapter 8, has a lattice energies that are greater than 600 kilojoules per mole, and sometimes with some of the larger charged molecules, it can be, or ionic compounds, it can be upwards of 10,000 kilojoules per mole. So we can get some pretty big numbers for ionic bonding. We're mostly going to ignore that in this chapter and look at these 4 different interactions. We'll find that the total strength of the intermolecular forces will determine the extent to which we get attractions between the molecules. So these do add together, and the stronger those interactions are, the stronger those forces are, the stronger the interactions, which will affect the properties. So we'll find that usually the strongest force will dictate the properties of the molecules. However, like I said, it can be a combination of more than one thing. So first, we want to start with London dispersion forces. London, if you're wondering where does the London come from, it was from a scientist whose last name was London, just in case you're curious. All right, so we're going to start with these dispersion forces, or London forces, or London dispersion forces, if you wish. We're going to start with actually helium. And helium turns out to be probably the worst example of London dispersion forces possible. That is, it's probably just the worst example. And that's because the dispersion forces in helium are extremely weak. If we look at it sort of under its normal conditions, So here we've got two helium atoms, and the electrons around the helium atoms are evenly distributed. So we don't have any polarization of that atom. Okay. Well, it is possible for the electrons to get temporarily unbalanced on that molecule, and when it gets temporarily unbalanced, we will find we'll find that there can be a small dipole that is created in that atom. Well, that means that there's a slight positive charge on one side of the molecule and a slight negative charge on the other side of the molecule, in this case just an atom. Well, it turns out that that slight and temporary, very temporary, we call it an instantaneous dipole, can induce a dipole in the next atom. So because this one is a little bit off balance, it causes the next one to be a little bit off balance. The negative charge pushes the negative charge in the next atoms a little bit over, and so we get an induced dipole in the atom. Well, we call this dispersion forces, and the ability of a molecule or atom to do this, we call it polarizability. Now, as I mentioned, helium is probably the least polarizable atom as an example, but it is a good example because we will find that dispersion forces are present in all molecules. So, so even though helium is very small and is not going to have very strong intermolecular forces, it is going to be present. It will have them dispersion forces present. So generally, we will find that dispersion forces are present in everything that has electrons, and that includes pretty much everything. Now, there are different factors that will affect how strong those intermolecular forces are. And the number one thing is going to be the size of the molecule. If we look here at helium, neon, argon, krypton, xenon, here these are all noble gases. They're all in group 7, or group 8 rather, going down, increasing molecular weight as we go down that list. We will find that as the strength of the intermolecular forces increases, the boiling point will also increase. So we can use boiling point as a pretty good gauge to determine how strong the intermolecular forces are. So as we increase the size, you will see that the boiling point also increases. We'll find this works not just for noble gases, but also for other things like fluorine, chlorine, bromine, and iodine are group 7 halogens. Right? As we increase the size, going down that list, we'll find that the boiling point increases pretty substantially. So the idea is that the larger the atoms are, the larger those electron clouds, or the larger the shells of electrons are, and therefore the more polarizable the molecules are. We'll also find that there is an effect from shape. Over here on the left, we've got N-pentane, which is C5H12. And over here on the right, we've got neopentane, and neopentane is also C5H12. For molecules that are like this, we call these isomers. So these are isomers of each other. They have the same number of carbons and hydrogens, have exactly the same mass, and so we might think that they would have the same strength of dispersion forces. But it turns out that's not quite true. The N-pentane has stronger dispersion forces than the neopentane. And we can account for this in terms of what the shape is. N-pentane is a long, skinny molecule and has a greater surface area. Whereas neopentane is a much more spherical shaped molecule. Now, it's definitely not perfectly spherical shaped, but it is a spherical shaped molecule. Well, we'll find that the longer and skinnier the molecule is, the greater the surface area, and the more spherical it is, the less surface area there will be. Well, we'll find that the more surface area there is, the higher the boiling point. So it becomes more polarizable and therefore has a higher boiling point. Whereas with the spherical molecules, it's less polarizable and has a lower boiling point. Now, it turns out that there is another isomer of pentane, and it's called isopentane, and it's also sometimes called 2-methylbutane. So there's 2-methylbutane, and you will see that it has a boiling point that is in between these two. It is somewhat linear, somewhat stretched out, but you'll see that there's a side chain here, and because of that side chain, it does have some of these spherical type properties. So we'll find that it's sort of in between those two molecules. All right, so we know that size and shape will affect the strength of the intermolecular forces. All right, next we want to look at the second type of intermolecular force, which is called dipole-dipole interactions. Dipole-dipole interactions are the interactions that we have, the interactions that molecules have because of permanent dipoles. If we look at acetonitrile has a polar bond between carbon and nitrogen. Nitrogen is much more electronegative than carbon, and so some more electron density is pulled towards that nitrogen. We can indicate that dipole either by putting the lowercase Greek letter delta plus and delta minus to indicate that partial charge. But we can also indicate that by putting a dipole arrow, and that indicates that there is a permanent dipole there. Well, that dipole causes there to be strong interactions. The partial positive of the carbon is going to be attracted to the partial negative of the nitrogen on the next molecule. And so we get a fairly strong attractive force. In solids, these forces add together pretty strongly, and therefore the molecules stay pretty much in place. In liquids, it's a little bit less organized, and so the molecules do have some of the repulsive forces, but the attractive forces definitely will make a big difference in this. So we will find that the stronger the dipole-dipole interaction, the higher the boiling point is going to be. And here we've got several molecules to illustrate this point. We've got several molecules that are approximately the same size. You'll see they're all have molecular weights here in the 40s. And the difference is the strength of the dipole-dipole interaction. And that strength of the dipole-dipole interaction, so here we've got the dipole moment of the molecule, 0.1, which is very, very nonpolar. Dimethyl ether here at 1.3, acetaldehyde at 2.7, and acetonitrile at 3.9. We'll find for molecules that are about the same size that they will have, the higher the dipole, or the higher the polarity, the higher the boiling point is going to be. So the more polar, the higher the boiling point. All right, so that accounts for dipole-dipole interactions. And so now we want to look at this particular graph. All right, so I'm going to start by putting these 4 compounds. Now, these are all group 4 compounds, and I'm going to come back and show you the periodic table real quick. All right, so here's our periodic table that we like to use. And when we look at that periodic table, we're going to look at carbon, silicon, germanium, and tin. Those are all in group 4. Here in a moment, we're also going to look at group 5, 6, and 7. And we're looking at binary compounds of these elements with hydrogen. So I'm going to go back and show you this. All right, so here we've got the 4 compounds that are in group 4. So CH4, SiH4, GeH4, and SnH4. Now I've drawn these molecules here on this piece of paper, and you'll notice that there are no lone pairs on the central atom, so none of these are polar at all. So really the only thing that will determine the boiling point of these is how strong the dispersion forces are. And that's simply because they get bigger as we go down that list. So as they get larger, we'll find that the boiling point increases. That is a completely normal, expected result. All right, well, now if we look at group 5 compounds with hydrogen, we'll come back over here and we'll see that in group 5, so here we've got ammonia, phosphine, there's arsenic. I forgot to put the lone pairs on the arsenic. Because of those lone pairs, all of those molecules are going to be polar. Now, they're not all equally polar, but they are all a little bit polar. So those lone pairs will cause it to be a little bit polar. Well, not surprisingly, for the most part, we'll find that the boiling point increases as we increase the size. But you'll notice for sure that ammonia, NH3, is an outlier. It does not seem to fall in that, and does not seem to follow that rule. All right. If we look at group 6, so H2O, H2S, H2SE, H2TE, again, we see the general trend that the boiling point increases as we increase the size. But water seems to not follow the rules there. It has a much higher boiling point than you would expect for something that small. All right, and here is group 7, these green ones, so HF, HCl, HBr, HI. And again, there is an increase in the boiling point as we increase the size, but HF seems to fall outside of the expected range. It's much higher. Well, the thing that causes this is a property that we will refer to as hydrogen bonding. So hydrogen bonding is merely a special case of dipole-dipole interactions, but it's an extra strong dipole-dipole interaction. The key requirements for having hydrogen bonding are: 1, you need to have hydrogen, of course. That hydrogen needs to be covalently bonded to either nitrogen, oxygen, or fluorine. And so you'll notice those are all in period 2 of the periodic table. Those are all in period 2 of the periodic table, which I'm going to point out here. All right, so there's nitrogen, oxygen, and fluorine. They're all in period 2 of our periodic table. All right, so here's ammonia, water, and HF, all in period 2 of the periodic table. And the reason that that is important is that the electrons in period 2 of the periodic table are very tightly held to those atoms. So they're very tightly held to the oxygen, the fluorine, and the nitrogen. Because they are tightly held and they are very electronegative, they have a fairly significant negative charge on them. And that makes the bond a special kind of dipole, and we will refer to it as hydrogen bonding. So we do get a hydrogen bonding interaction between the molecules. We do have to have a lone pair of electrons because that's where that negative charge, partial negative charge, is going to be. So we do have to have that lone pair of electrons on a nitrogen, oxygen, or fluorine, and we get a hydrogen bonding interaction. Now that hydrogen bonding can be between molecules that are different, or it can be between molecules that are the same. You'll see for these first 3, these are all hydrogen bonding for molecules that are the same, but you can see that we get hydrogen bonding between molecules that are different as well. All right, so let's look at number 14 on the in-class assignment. All right, so number 14, what type of intermolecular forces are common to these? So we're saying, what type of intermolecular forces can we get between this and this? Well, just as a reminder, everything can have dispersion forces. So I'm going to go ahead and put this can have dispersion forces. right? So we can definitely get dispersion forces between those two things. Now, in order to get a dipole-dipole interaction, we need to have both of them be polar. Well, methanol is definitely a polar molecule. However, xenon is not. It's just a single atom, so it is not polar. So that means that there are no dipole-dipole interactions. Well, if there are no dipole-dipole interactions, that also means that there are no hydrogen bonding interactions as well. So we're only going to have dispersion forces for that one. For B, of course, we're going to have dispersion forces because everything that has electrons has dispersion forces. So we'll go ahead and write that down. All right, and then here we've got methanol and acetonitrile. Well, I'm going to sketch out what methanol and acetonitrile look like real quick. So you saw acetonitrile just a little bit ago. All right, here's methanol, and then there is acetonitrile. So there is acetonitrile. And we need to have a hydrogen that is covalently bonded to either nitrogen, oxygen, or fluorine. So yes, this counts. And on the other molecule, we need to have a lone pair of electrons on either nitrogen, oxygen, or fluorine. So we do have that lone pair of electrons, so we can get a hydrogen bonding interaction between those. So yes, this is capable of doing hydrogen bonding. So this one, it will have dipole-dipole because they are both polar. And it will also have the hydrogen bonding, which I'm just going to call H bonding. All right, for ammonia and HF, I'm going to go back to our page here, and ammonia and HF. Turns out there's two different ways that we can draw this. Here's ammonia. All right, well there we have hydrogen that's covalently bonded to nitrogen. And then on HF, we have hydrogen that is covalently bonded to fluorine. Well, because there's a lone pair on the nitrogen here and a hydrogen that's on the fluorine, we can get a hydrogen bonding between those two. But we can also get this going the other way. That is, if we had HF and NH3, well, this hydrogen is capable of hydrogen bonding, and we've got lone pair electrons on that fluorine, so we can get a hydrogen bonding interaction between them that way as well. So not only are both of these polar, so we get dipole-dipole interactions, but we also get hydrogen bonding interactions. So we'll get all three of them. Dispersion forces, dipole-dipole, and then finally hydrogen bonding. All right. So now we'll find that the hydrogen bonding interaction is especially important for how it affects a lot of different things, including water. We'll find that one of the features of water that you're probably familiar with is that ice is less dense than water. Most of the time, when you have a solid of a compound, that solid is more dense than the liquid. But that's not the case with ice. Ice is less dense than water. So as a consequence, we will find that ice will float on top of water. If we look at the density, it's a pretty significant difference of about 8%. And that is enough to cause all kinds of interesting arrangements. You can see here, if we freeze a bottle of water, the water will expand and sometimes even cause the bottle to rupture. Okay, so that is for hydrogen bonding. Our next type of intermolecular forces is called ion-dipole interactions. And here, in order to have an ion-dipole interaction, we need to have an ion and a dipole. Again, that seems kind of obvious, but here we've got the negatively charged chloride anion, and it is attracted to the partial positive charge on the hydrogens. And then here we've got the partial negative charge on the oxygens, and it is attracted to the positive charge on sodium. Well, these can have a fairly wide range, but they're generally pretty strong. And we will find that this is one of the things that allows many ionic compounds to dissolve in polar solvents like water, is this ion-dipole interaction. So you just need to be able to recognize when we're going to have ion-dipole interactions. All right. And then here is a chart of the different ions, and we saw this. We saw something like this. I went through these a little bit earlier, but this kind of breaks it down into what the different categories are. And then these are those energies that I mentioned last time. All right, so we want to look at numbers 16 and 19. All right, so here on number 16, we want to see what type of intermolecular force accounts for the following differences in each case. All right, well, there's methanol and then CH3SH. So here is methanol, and CH3SH looks very similar. The only difference is that it has a sulfur in place of the oxygen. Well, we might expect, because that sulfur is so much larger than oxygen, we might expect it to have a higher boiling point. However, that's not the case. If we look at methanol, it has a boiling point of 65 degrees, whereas the thiomethane has a boiling point of about 6 degrees, so it has a lower boiling point. Well, the reason for this difference is because of hydrogen bonding. So CH3OH is capable of hydrogen bonding. All right. Xenon is a liquid at atmospheric pressure and 120 Kelvin, whereas argon is a gas. Okay. Well, to illustrate this difference, I'm going to bring the periodic table back over. So we're comparing xenon and argon. So there's argon, there's xenon. Since xenon is much larger than argon, we would expect it to have a higher boiling point. And that's definitely the case. At 120 Kelvin, we'll find that this one's a liquid and that one is a gas. That means that the boiling point of xenon is somewhere above 120 Kelvin, and that the boiling point of argon is somewhere below 120 Kelvin. So xenon is larger and has stronger dispersion forces. All right, next we want to compare krypton and chlorine. Krypton, atomic weight 84, 120.9 Kelvin. Chlorine, atomic weight 1, 238 Kelvin. So even though chlorine is smaller than krypton, chlorine has a higher boiling point, so it must have stronger intermolecular forces. Well, since krypton is atomic, and chlorine is nonpolar, we'll find that we cannot have any dipole-dipole interactions. So the key, the key difference here between krypton and chlorine is that krypton is just an atom, so it's just a sphere, whereas chlorine is a molecule. And because it's a molecule, it has more of a rod shape to it. Well, as you remember, molecules that have rod shape to them that are more linear have a larger surface area, and therefore can have stronger dispersion forces. So Cl2 is more rod-shaped. And therefore has stronger dispersion forces. All right, now let's look at acetone versus 2-methylpropane. Well, acetone, right off, you can see these are about the same size. Acetone has a higher boiling point, therefore it must have stronger dispersion, or must have stronger intermolecular forces. Well, acetone, as you can see, has that carbon-oxygen double bond, and that carbon-oxygen double bond is quite polar. Whereas in 2-methylpropane, it only has bonds between carbon and carbon, or between carbon and hydrogen. Because of that, it is not very polar. So since acetone is polar and the 2-methylpropane is nonpolar, we will find it has stronger intermolecular forces, and therefore it has a higher boiling point. So I'm just going to put acetone is more polar than 2-methylpropane. All right. And then let's look at number 19. So here on number 19, which member of the following pairs has the larger London dispersion forces? Here we are looking exclusively at which one has stronger dispersion forces, not necessarily at which one has stronger intermolecular forces. Well, the stronger dispersion forces between H2O and H2S, here size is going to pretty much dictate this. So H2S, because it is bigger, will have stronger dispersion forces. CO2 versus CO, well, clearly CO2 is bigger, so it will have stronger dispersion forces. And then methane versus silane, so the CH4 versus SiH4. SiH4 is bigger and therefore will have stronger dispersion forces. All right, when we're trying to compare intermolecular forces, if they have comparable molar mass and shapes, then dispersion forces should be roughly equal. If molecules have very different molar masses and there's no hydrogen bonding, then we'll find that the dispersion forces will determine which one has the stronger intermolecular forces. All right.